Hello, and welcome to Physics for Play. In today's episode, we're going to mix things up a little bit. Instead of talking about our usual physics examples, we're going to show how you can use the physics idea of entropy to perform really well in the game Wordle. Let's get started. So, if you are unfamiliar with Wordle, it's a very simple game. The basic idea is you are trying to guess a 5-letter word, and every time you guess that, you make a guess for that word, you get some information about what the word actually is. So you can only guess 5-letter words, and suppose your first guess was the word weary, you get some information back about that word. If the letter of your guess appears in green, that tells you that letter, in this case W, is both in the word and it's in the correct position. So it would be the first letter in the word. If you guess a word and one of the letters appears in yellow, that would mean the letter is in that word, but it is in the wrong position, so that we know that there must be some other letter in that second position. And if the letter comes back in gray, we know that the letter does not appear anywhere in that word. So to begin, we're going to select a corpus of 5-letter words. And I am told that you can find the list of 5-letter words by going to this site here. As you can see, they've been encrypted to prevent spoilers. So we are going to need to get rid of that encryption. It's encrypted with ROT13, which basically means you rotate the letters by 13. So for example, if the letter was supposed to be the letter A, you are going to rotate the alphabet by 13, so you'd go 13 letters after the letter A, and that would be your next letter. So I'm going to go ahead. I've downloaded these Wordle answers to my desktop. We're going to import this text file as data, and I'm going to put that list into a variable that I've called dummy. And then I'm just going to break that encryption by rotating these. I've defined this rule, which does an ROT rotation of the different letters. We're going to rotate by 13, and we're going to rotate all of the letters in dummy. So we're replacing the letters that are there with the actual letters in the letters that will be in the real word. So we'll run this code really quick. And you'll see there's a bunch of 5-letter words here. And I'm told that this is the corpus of words that is used by Wordle. Now, if we go ahead and look at the length of that list, you can see there's a little over 2,300 words, so quite a few options for you to choose from. Now, you might think that all guesses are equal. And while it's true that we can probably make the assumption that any word is equally likely, it is emphatically not true that every word is an equally good guess, because we get different information depending on our guess. Again, we get information about what the actual word is depending on what word we guess. So not all words are created equal, and you can see that because not all letters are used equally as often. So if I take my list of words and I join them all together and I count the letters that are in them, you will see that E is the most common letter, followed by A, followed by R. So you're going to see a lot of vowels at the front of this list. Followed by O, followed by T, and then, as you'd expect, the least common letters are things like Z, X, Q, and J. Now, statistically, the letters at the front of this list appear more often than the letters at the back of this list. And that's about what you'd expect. You'd expect your vowels, your E's, your A's, your O's, and some of your more common consonants like R and T to appear more often, whereas your Z's, X's, J's, and Q's are going to appear less often. And what that means is that letters that contain more common letters are better guesses. Even though each individual word is equally likely to appear in the Wordle puzzle, guessing words that have more common letters is going to get you more information because, again, you will learn if a letter is in the right position, if it's in the word or if it's not in the word. And that's the information you want to pull out with your first few guesses. So you can imagine you might want to guess words that contain these common letters. Things like orate, raise is a common one that has a lot of vowels and common consonants. The word stare, like I'm staring at you, would be a common one since S is pretty common and T is pretty common. And we could do this just based on we could do this based on just the frequency of letters, and we could assign a score to that. But we could just also count, and we could take a much more physics-based approach and just count statistically, if I guess a word, how many more words is that guess going to eliminate? On average, how many words of the 2,315 am I going to eliminate by making a given guess? And that approach we are going to call entropy reduction. Now, you may have heard of entropy in the context of thermodynamics, where the second law of thermodynamics says that entropy is always increasing. And you may have also heard that entropy is a measure of the amount of disorder in a system. That's one way of thinking about entropy, but it's not the one I prefer. I prefer to think about entropy in the context of information, where the entropy is the amount of information you don't know about a system. So if you're thinking about the gas in a room, the entropy is the amount of information, in this case, the positions and momentums of all the particles that I don't know. So I might know just the average pressure and temperature, but I don't know specifically where all the particles are. And information entropy is the same whether you're talking about an ideal gas or whether you're talking about the number of words in a Wordle problem. So here our goal is going to be to reduce the amount of entropy, in this case, the amount of information I do not know about the words that the answer could be. So starting off, you could think of your entropy as being 2,315 words, and I don't know which of those words it could be, but we can eliminate some of those words based on the guesses because we get new information with every guess that we make. So let's go ahead and try to guess a word and see how we can use the concept of entropy reduction to maximize our likelihood of winning at Wordle. So I've got a second screen here where I've just made my first guess. And my first guess is the word raise. And you can see that from the word raise, I've guessed the letter R correctly. However, the letters A, S, and E don't appear anywhere in the word. And the letter I appears somewhere in the word, but it's not the third letter. So I'm going to go ahead and I am going to select from my words. I am going to select something that contains the letter I. And we'll start we'll start with just containing the letter I, and we'll put the rest of the information in a second. But let's figure out how many words I have that contain the letter I. And remember, we're starting off with 2,315 words. Let's see how much our entropy is reduced. So you can see we've got a lot of words here, and I'm going to just look at the length of that list. So already I've reduced the number of words I have to about 647. So that eliminates a lot of words. Now let's look at the letters I don't have. So I'm going to also include, I'll use the double and symbol to say I want to include the letter I. And I want to not have, so this exclamation point means not. I want to not have the letter A, S, or E. So we'll throw those in there. Oops, too many ands in there. So that gets us down to 214 words. So that's a little bit better. Now, I have the letter R, but I specifically have the letter R in the first spot. And if we look at our list of 614 words, or 214 words, you can see the vast majority of words that I have left do not have the letter R in the first spot. So that's already telling me something useful. So what I am going to do, I'm going to make sure we have the letter R in our first slot. So here, so far I've only used the function string contains. So that means the letter has to appear somewhere in the word. I'm going to do, to make sure that the letter R appears in the first spot, I'm going to use two functions. I'm going to use a string matching function, and I'm going to use regular expressions. So if you're unfamiliar with regular expressions, it's kind of a generic way of writing strings where you want to have certain rules between the strings to get them to match. We could do a whole video on this, but there's plenty of other videos that already do a better job than I would do. So I'll let you look that up on your own. But we are going to find something where the first letter is R, and I'm going to represent the rest of the letters just by underscores here. And the rest of this code is really just to get, the rest of this string replaces just to get the regular expression to look like it's supposed to with the your slash uppercase D. But once I execute this, you should see I only have words that have the letter R in the first spot. So I'm going to go ahead and do that. And you can see I've already reduced my list to only 5 words. And in fact, it's going to be better than that because there's one more bit of information I haven't taken into account yet. And that's the fact that this letter I cannot be in the third spot. And you can see I have a word here, rhino, that has I in the third spot. So I want to make sure I get rid of that. So I'm going to go ahead and eliminate rhino by doing another string match. So I'll do the same thing here. I'm just going to copy that. Except this time, I can't have an I in the middle spot. So I'm going to put an I in the middle spot here, and I'm going to put a not here. So I am not going to be matching this. And if I do that, I should get the same list of letters back this time, or list of words back, this time with only words that do not have an I in the middle spot. Now, I've got a 1 in 4 chance, because now my entropy has been reduced just from one guess. I've reduced it from 2,315 words to I've got a 1 in 4 chance now of guessing the right word. So what do I want to do here? Well, I'm gonna actually join these all together. I'll do string join. Let me join all of my remaining words left. And I'm going to just count the number of characters that are in there. So I'll say character count. or character counts. You can see there's a lot of them have I, a lot of them have R, some of them have G, so I probably want to guess a word with a G in it. Or letter O. Let's see, if I guess G, 3 of the words have a G in the middle, but if I guess O, that will break only 2 of the words have an O in it. So I'm gonna guess a word with an O in it, and we'll see what happens. So I happened to guess lucky, because Robin was the correct word. But you might be thinking, how do I optimize my guess? So how do I make the guess that is going to reduce the entropy the most? And we're going to talk about that now. So our strategy is going to be, we want to guess the word that leads to the largest reduction in entropy, i.e., the word that statistically is most likely to eliminate the largest number of words from contention. So to do this, we're going to set up a few different functions. And I've taken the liberty of writing these functions out ahead of time. So the first function we're going to get, actually, before getting to the first function, it's important to there's 2 bits of information that are relevant here. There's what your guess is, and then what the answer is. The guess you have control over. That's what we're trying to optimize. What guess do I choose? The answer is an unknown variable, so that's where our entropy creeps in. There are only certain answers that can be correct, and we don't know what those answers are, but we know what they can be. We don't know what the answer is, but we know it's a list of 2,315 words. So I put this function together. This is the information you learn after a given guess. I won't go through the full function. I'll just show you roughly how it works, because it's going to output what letters do you have to include, what letters do you want to exclude, what are the known correct letters and what are the known wrong letters. So I'm going to just run this code, and we're going to put in a possible guess and an answer. Suppose my guess was raise. Suppose my answer was Robin. And what this will tell me is it'll tell me the letters that have to be included. So this is, we show that it contains the letters I and R, and you can see both the guess and the answer contain I and R. It tells me the letters to exclude, and you can see that from our guess, the letters A, E, and S are excluded. It tells me the letters that are in the correct spot. So R was in the correct spot. So these are the known correct letters. And these are the known wrong letters. And by wrong, I just mean that they're in the wrong spot. So I know that the third letter cannot be the letter I, because as we saw, I does not appear in the answer in the third spot. So it shows up as yellow in your Wordle function. So our first function told us what information was learned when you make a guess. The next function we're going to look at is going to tell us what words remain. So you make a guess, how many words remain, and what are those words? So I'll throw that function here. So based on your guess, based on the current remaining words, so how many, after each guess, you're going to update the current remaining words. And we'll also input the answer here. we are going to figure out what words remain for a given guess, a given answer, and a given set of words that remain. So I'll go ahead and evaluate that. So again, we're going to take the guess. We're going to guess the word raise. The answer is going to be robin. And the words that remain, I'm just going to put all of the words from my list in the words that remain. So if I run this code, you can see, as we did before, we only have 4 words that remain. However, if I were to change the answer, so suppose the answer wasn't robin, suppose the answer was eagle, what you would see is that more words would remain based on that list. So what I've done here is I've used the information learn function to figure out what words are going to remain when I make a specific guess. So to recap, our strategy is we're going to guess the word that leads to the largest reduction in entropy, i.e., we're going to find the word that statistically is going to eliminate the most words from contention. To do that, we've constructed a function that tells us what information we are going to learn for a given guess, assuming we know what the answer is. So for a given guess and a given answer, what information do I learn? And that's going to tell me what letters do I include, what letters do I exclude because they're not in the word, what letters are in the correct position, and what letters are correct but they're in the wrong position. Using that information learned function, we're going to figure out what words remain. So of all the possible words, it could have been which ones are still viable options after I make a certain guess. And the only problem is that we don't know what the answer is. So what we're going to do is we're going to test every possible answer and figure out, on average, which guess is going to lead to the largest entropy reduction. If I average over all of the possible answers it could be, I can figure out which guess is most likely to give me the most information. So we're going to compute the average entropy reduction for a guess. And to do that, we are going to make a table of all the possible remaining words. And for a given guess, we're going to figure out what words remain for that guess. So for example, when I guessed the word raise, we found that there were only 4 words left, one of which was robin. But there were only 4 words that remained after I guessed the word raise in today's Wordle. We're going to figure out what the length is of that, so that'll be 4. But we're going to do that, since we don't know what the answer is, we're going to do that for every possible answer, and we're going to take the average of it. So I'll go ahead and compute that code, run that code, and then we'll test it out with, I'm going to test it out with 2 different words. I'll test it out with the word fuzzy. Now fuzzy is probably a bad guess. Fuzzy is probably a bad guess because if I look at all the possible letters from all the possible words, the word fuzzy has 2 Z's in it, and Z doesn't show up in very many words. It also has an F, which is not super common, and a U, which is which I think is the least common vowel. So fuzzy is not going to be a very good guess, but we'll see how many words remain after I run fuzzy. And I'm also going to run the word stare. And we can see, here we go, we've got our answer here. Now this code will take a little while to run because it's looping through all of the possible words. But on average, if you guess the word fuzzy for your first guess, you are going to reduce the number of possible answers from 2,315 to about 855. Now, I can do the same thing for the word stare, but stare is going to be probably a better guess because it features more common letters like E, A, R, T, S. So I am more likely to get useful information out of guessing a word that has more common letters. So I'm probably going to reduce our entropy, i.e., we're going to statistically be more likely to eliminate more words from contention. So again, this is going to take a while. It looks like it's done. And what you can see here is a word like fuzzy. Well, you still have over 800 words left, but if I guess a word that has more common letters like stare, you've only got 71 possible words left on average. So stare is more likely, it's statistically likely to be a better guess. Now, what you can see here is that we can do this not just for a couple of words, we could do this for every possible word. So we could figure out of all the words that I could guess, which one is going to lead to the largest entropy reduction. So we are going to do that now. We are going to find the guess that optimizes entropy reductions. So right now, for a given guess, I loop through all of the possible answers. Now I'm going to loop through all of the possible words. So I am going to post this code here. So we're going to compute the average entropy reduction for a given guess. And then I'm going to make a table of all of the possible guesses that I could make, along with how much the entropy was reduced. And we're going to sort that table. So I am going to go ahead and run this, but I'm going to pause the video because this is going to take a while to run. So we'll be back in a little bit. Okay, we're back. What you can see here is that we've got our answer. The best possible word to guess, based on the corpus that we used of different guesses, is the word raise. Because if I guess the word raise, on average, I only have about 61 words remaining. Fuzzy, it turns out, was the worst possible word I could have guessed, because you're still going to have 855 letters that are left. Mummy is also a bad word because it only has 3 letters in it, so that's not very useful. Vivid is a bad word. V's aren't great letters to use. But you can see the best possible words are the words that have the common letters. Things like raise, arise, irate. These are words that are going to give you the largest entropy reduction, which means that statistically they're going to give you the best, most useful information for your guess. So that's all we'll cover for today. Hopefully you enjoyed this video. Like it if you liked it. And if you'd like to see more of these, please click subscribe.